Good morning. We are going to deal with the third module of design and analysis of algorithms. Let us start with depth first search and breadth first search. You have already learned about these topics in data structures and you will have an idea about what it is. Let us try to recollect what you have learned. Graph is basically represented using G is equal to V comma E, where V is the set of vertices and E is a set of edges. Basically, there are two standard ways to represent a graph. It is using a adjacency matrix and an adjacency list. The representation of an adjacency matrix is in the form of a 2 by 2 matrix which has V number of rows and V number of columns also, where V is the number of vertices in that graph. Now to represent the adjacency matrix, it can have values only 1 and 0. For example, we can explain it with an example. This is a directed graph which has some edges between vertices. Not all are there. So there is, in this example, 1 is a node which has an outgoing edge to 2 as well as to 3. 2 is having an outgoing edge to 3 as well as 4 is having an outgoing edge to 3. 3 doesn't have any outgoing edges. So the adjacency matrix also has only 4 edges or 4 ones. In this, there is a 1 between a 1 to 2, first row, second column, as well as there is first row, third column 2. That means there is a edge between 1 and 3. Similarly, there is an edge between 2 and 3. That means second row, third column, 4 to 3, fourth row, third column. You can just go through that. The row in 3 is all zeros. It doesn't have any edge going outward. Similarly, you can represent the graph in another way also. It is adjacency list. In this, it shows the adjacency list means by the name itself, as you can understand, it shows the adjacent edges to a particular vertex. In this list, adjacent of 1 is equal to 2 comma 3. That means node 1 has a node towards 2 as well as to 3 also. Similarly, 2 has a edge towards 3. 3 doesn't have an edge going outward. 4 has an edge towards 3. So adjacency of 4 is equal to 3. Now, traversing a graph means you have to travel through each and every vertex using the given edges. You may be remembering in tree there are traversing methods like in order, pre-order and post-order. These are 3 different ways how you can traverse through all the nodes inside the tree. Similarly, in a graph there are 2 different ways. It is breadth first search and depth first search. From the name itself, it is very clear that breadth first search means the traversal will be going breadthwise, and in depth first search the traversing will be going depthwise. Unlike from tree has a root node, but in graph you will have to specify from which node you have to start. Now, why is this traversing a graph so important? The applications fall in gaming as well as in computer networks as well as in practical implementations like Google Maps and so on. The basic idea in both these traversing's are a vertex progresses from an undiscovered state to a discovered state and then to a completely discovered state. In the previous sessions, as in data structures, you learned the breadth first search and depth first search using 2 variables known as visited and unvisited. Try to recollect that. The same concept is used here using colors. Here, the states of the node is represented using 3 different colors: white, gray and black. White represents undiscovered, gray represents discovered and black represents completely explored. White means it has to be moved and it has to go to all the states. Gray means it has just visited, but the traversing has to go on. Black means whole concept, no more revisiting is done. Completely it has been explored. To say about more about the colors, white vertices have not been discovered all the vertices start out with white. Gray vertices are discovered but not fully explored. They may be adjacent to white vertices. Black vertices are discovered and fully explored. They are always adjacent only to black and gray vertices. That means a white vertex has to go to a gray and only then to a black. Black will be always associated with gray or black vertices. Now, from going deep into the traversing of a graph, the process is like this. It starts with a single vertex and evaluates its outgoing edges. If the edge goes to an undiscovered vertex, mark it as discovered and add it to the list of discovered vertices. If an edge goes to a completely explored vertex, just ignore it. You don't have to go and then traverse it once again. So its transitions are always has already been completed. If an edge goes to an already discovered vertex, that also has to be ignored. The analysis is not so complicated. It has to visit all the vertices as well as it has to go through the edges it has been marked for. So analysis or the time complexity will be big O of number of vertices plus number of edges. Now let us go into detail into the breadth first search. Breadth first search is one of the simplest algorithms for searching a graph. Given a graph, G is equal to V comma E, where V is a set of vertices and E is the set of edges, and a distinguished source vertex S. As we already said, graph doesn't have a beginning. You will have to specify a source or a source vertex from where the traversing has to be started. Breadth first search systematically explores the edges of G to discover every vertex that is reachable from S. Now, the algorithm discovers all vertices at distance k from S before discovering any vertices at a distance k plus 1. It's very clear from the sentence that if you want to find out a vertex in the level k plus 1, it has to surely or mandatorily cover the vertices in k, all the vertices in k, in the level k. That is how it becomes breadth first search. In the level 0, if the starting node S is considered to be level 0, the next level 1 is considered to be breadth wise, and all the vertices in that level has to go through, only then it will be gone to the next level. Now, to keep track of progress, breadth first search colors each vertex white, gray or black. All vertices start out with white and may later become gray and then black. A vertex is discovered the first time it is encountered during the search. At that time it becomes non-white. This we have already discussed. Now in the algorithm there are basically three different arrays which keep track of where we stand, whether we have explored, whether it is in the discovered or undiscovered state, and so on. The first array is color of U. The color of each vertex U is stored in the variable color of U. This color of U for a particular vertex can hold white, gray as well as black. White means it is in the initial case color of U will be always white. Once it has started traversing it becomes gray, and once it has completely explored it becomes black. The predecessor of U is stored in the variable pi of U. From where did it come? Who is the predecessor of U? That is being stored in pi. The distance from the source S to the vertex U is computed by the algorithm and is stored in d of U. Now, being the distance source is considered to be 0, and in the next level the distance of U will be 1, then the distance below that will be 2. So at what distance are we standing from the source is stored in d of U. Now this is the algorithm. Let us take a look at this algorithm. The first part of the algorithm, it is initializing every node inside the graph for each vertex u belonging to v of g minus s. Now s is the source and u are the all the vertices other than the source. So color of u, for every u other than the source, everything is put to white, d of u is put to infinity, and pi of u is nil for the time being. Next, starting the traversing, color of S is made gray, that is you have started exploring. D of S, distance from the source, is 0, pi of S, naturally it is nil. It doesn't have a predecessor in the beginning. And there is a data structure Q, which is basically a queue. Initially it is empty and it is represented using a phi. Naturally the operations on a queue are NQ and DQ, that is insert into a queue and taking out of the queue. NQ Q comma S means S is put into the queue. The nodes which we traverse through is put into the queue, and once it is completely explored, it is removed from the queue. This is what is done here, putting a color, adding the distance, and taking it out of the queue. Now the while loop, you can go through and you can just find it out. Q not equal to phi unless and until the queue is not empty. You have to take the adjacent nodes of the node under consideration, the colors of which are white, it has to be made gray, the distance has to be added up, and the predecessor has to be added and put into the queue, and it goes on. Unless and until there are no more adjacent edges to that particular node, this goes on, and later on it is made black. Now next, this is how to print the path. Print path g comma s comma v. If v is equal to s, if the current node is equal to s, then print s. It has only one node. Else, if pi of v is equal to nil, that means it is only the source. So there is no path from s to v. Else, you have to print all the path from s to v, which is already stored in the array pi of v. Now let us explain this using an example. Breadth first search, there is an example. In this example, there are 8 nodes named from R to Y, R, S, T, U, V, W, X, and Y. From this, it is very evident that R is adjacent to S as well as to V. S is adjacent to R, W. W is adjacent to S, T, and X. T is adjacent to W and X. T is to U also. U is adjacent to Y and T. Y is adjacent to X and U. X is adjacent to T, W, and Y. You can take n number of paths. Now how do you go breadthwise? So the source that we will start here is from S. So S has an adjacent edges to R as well as to W. So taking that, S is made gray. As S is the source node, the distance is put as 0. It is put into Q because it is a node to be considered. Later, S has become black. The gray was turned to black. The distance is the same. It takes the adjacent two vertices, that is R and W. You can take either R first and W next, or W first or R next. In this case, we have taken W first and R next. It doesn't have, because both are having distance 1 only, so you can take it in any order, no issues in that. But here we have taken as W and R. So the color of R and W is gray, and the distance has been added as 1. Why? S is 0 from S. The distance to R is 1 node. Similar to W is also 1 node. So that is why it is 1. And W and R has been put into the queue. Now next we'll consider from W, because W was the first element, that was the Q. Now that W will be put as black, and the adjacent nodes from W will be taken into consideration. Again, here it can be X or T or T or X. Anyway, that's okay. Now in this case we have taken T comma X. So the distance from the source is 2 towards T as well as 2 towards X also through W. T and X is inserted into the Q. Now next we have to consider R. It has to be taken from the front. So taking R into consideration, R has an adjacent node as V. The color of V is turned to gray. Distance is added up to 2 and V is added into the Q. Next we have to take T, because that was the first that was put in the Q, and T's adjacent is only U, because X is already taken. You don't have to add up X again. Undiscovered has to be considered, so it will be taking U. So the distance from the source to U is 3, that is S to W, W to T and T to U. So the distance is 3 there. It has been made gray and it has to be added to the end of the Q. Next we will go for X. X is having a value 2. So that was in the Q also. That has been made black. The adjacent to X is taken. X has three adjacents. One is to T, one is to W and one is to Y. T and W is already considered. They are being put as black, so that they needn't be considered once again. The unexplored Y will be taken, that is pushed into the Q. It is turned to gray, partially traversed, partially considered, and the distance will be taken or added up to 3. Next, the node to be considered is V, because that is the first in the Q. Again, that becomes black. It doesn't have any adjacent. The one adjacent is R, that is already black. It has to be ignored. So you don't have to go further. Next in the Q is U, that is made black. Already adjacent to U, all the nodes have been taken under consideration. Thing is white, so it has to go on. And in the last one in the Q is Y. Now this becomes empty. So this is the way how breadth first search is implemented, and you can see that all the colors in the breadth first search, the nodes which has been visited, or in the other words you can see it as it has been explored, are black, and the distances are also there. So from S to any particular node, which is the path it has gone through, that is going on updated in the pi array, and that can be printed out. So that's the end of this breadth first search. Thank you.